So welcome everyone for today's session on achieving results, operational excellence. Today's session, we're going to talk about Six Sigma. And again, what we're trying to do is we're trying to provide exceptional value to our customers and simultaneously improve our business performance. So Six Sigma is another technique we can use. And what I'm doing is I'm looking to try to get breakthrough improvement. So breakthrough improvement is significant improvement over our current operations performance. So we're looking 50%, 80%, that type of improvement in performance for the organization. So these are techniques to do that. We already talked about theory of constraints in session 1. We talked about lean in session 2. In session 3, we're going to talk about Six Sigma. So let's talk about what Six Sigma is, a definition. So I use a definition from ASQ, which is a method that provides organization tools to improve the capability of their business processes. This increases in performance and decreases the process variation. It helps lead to defect reduction and improvement in profits, employee morale, quality of products or services. So Six Sigma is focused on the process and trying to reduce variation that causes us to not meet either our customer requirements or the business requirements. I think we talked in session 1 about theory of constraints, about the requirements for the business and the organization, and also customer focus we talked about in the lean session. So we want to focus on the customer. We want to understand what the needs of the customer are. We want to understand what the needs of the business are. And then, of course, if we're not meeting the expectation, it's typically due to excessive variation. So Six Sigma is a technique to help us reduce that variability in the process or the system. So there's 2 types of methodologies for Six Sigma. The first one, what they call the DMAIC method, which is the steps of the process are define, measure, analyze, improve, control. And this is really used for improving existing process or system performance. So if you have an existing process in place, an existing system, you're going to use the DMAIC method to improve that performance. Now, there's also one for designing new products or new processes, which is similar in the first 3 steps, but at the 4th and 5th step are different. So it's define, measure, analyze, design, and verify. So if you're designing something new, you're going to use that process. 90% of what I see companies using are using the DMAIC process for process improvement, define, measure, analyze, improve, control. So what we're going to do in this process today is go through these different steps. What are they? What techniques do we use in those steps? And then what are we trying to achieve with each step? So what Six Sigma is not, so it's not just about statistics. A lot of people think, oh, it's like all we do is statistical analysis. That's a piece of it, but it's not just about that. It's a quality program. So it's not a program where you start and finish. It's a continuous process of systematically going through and looking to reduce variability in your system or process. It's only for technical people. That's not true. It's for anybody in the process. So anybody in the process can use these techniques to improve the process. It's used when a solution is known. So it's like, oh, we already know what the solution is, so let's get the data to support the solution. No, it's not used for that, and only used for firefighting. So it's not used for firefighting. It's to get the process stable and capable. We'll talk about what that means. So in our first session, we talked about systems. So I want to review this again if you missed the first session. But what is a system? So a system is an organized, purposeful structure that consists of interrelated and interdependent processes. So there's multiple processes that make up a system. The output of one process is the input for the next process. So that's the dependency. So the second process here is dependent on the first process. The second process can't do their work, so the first process completes their work. Now, if that process doesn't give this second process what they need, then that's a problem. So then if we're looking at the second process doesn't have all the sufficient things to do their work, then that's a problem. We can use Six Sigma to address that. And also the interrelationship. So actions in one process can have positive or negative actions in other processes or functions. So a lot of times I see conflicts between functions. So purchasing isn't in alignment with operations. So they don't bring material in on time. So then we're expediting to get material in. or engineering doesn't put all the specifications that are needed, and then purchasing is buying stuff out of spec. So there's interrelationships. So if something's missing in one department, it can cause negative effects in other departments, and that negative effect typically goes down the chain until it hits the customer. Okay, so what we're looking for is where are those interrelationships and interdependencies that are not working so well and causing problems. So a system is a combination of different processes. Multiple processes make up an organization. All organizations can be defined as a system. And so I'm all about system thinking. So we want to be able to understand the system and understand what's preventing the system from getting better performance. Of course, what causes us to not meet our customers' requirements, and the customer doesn't mean the external customer, it can be the next step in the process, internal. So we have internal customers and external customers, and we have variation. So every process has variation. We can't have zero variation in a process. So the goal of Six Sigma is to reduce that variation of the process. So what is variation? So the simple definition is the difference between what we get and what we expect from the process. So we have an expectation of what the process is supposed to deliver. And then after we run the process, we measure what was actually performed and what was actually delivered, and does that meet the expectation? So a lot of ways to think about this is like a print. So if I have a print that I'm making a part to, that print has a nominal dimension I'm trying to hit, and it has a tolerance. So the tolerance is the acceptable variation. So if I make a part, I measure it. Of course, we never get exactly nominal. We get something close. The question is it within that acceptable range or not? So if it's within the acceptable range, that's acceptable variation. If it's out of spec, which is outside the tolerance, then that's a problem. Because we all know that stuff happens, right? So variation is a cause of all the problems that happen throughout the day. So Six Sigma is focused on this variation, and what can we do to reduce that variation? So there's two types of variation. So the first one is what we call common cause. So common cause variation is inherent in the process. So we can't reduce it unless we change the process itself. The second type of variation is what we call special cause variation. And this is variation that's unpredictable and happens sporadically. And we call it assignable cause because we can assign the reason. So one of the biggest mistakes I see in companies is they misclassify the type of variation that they're looking at. And there's certain techniques to deal with common cause variation. There's certain techniques to deal with special cause variation. And of course, if we misclassify it, we're going to be taking the wrong actions, and then the problem never gets solved. So I'll give you a quick example. I just did some problem solving training for a company that makes cylinders for the automotive industry. So the cylinders that they make, they basically machine it, and then there's a piston that goes inside this cylinder that has to have a certain surface finish inside the cylinder. Otherwise, the piston won't seal and it'll leak. So they measure the RA, the surface finish inside that cylinder, and what they found was that in the first eighth of the cylinder wall, it was out of spec for the RA. So the surface finish was out of spec. It was too rough. So we start going through the problem solving process, and we say, okay, here's the definition of common cause and special cause. And I asked, do you see the RA out of spec on every part? No, it happens sporadically. And sometimes it's good, sometimes it's not. Okay, so what type of variation will we expect? Well, if it's a sporadic problem, it's special cause. So I said, okay, what did you do to try to address the problem? So, we made a bunch of process changes. We changed the feeds and speeds. We changed the direction of the coolant. We changed the pressure of the coolant. I go, those are all process changes that we do when we have common cause issues. So you use common cause techniques to address a special cause problem. What's the chance that you solve this problem? They said, well, based on what you just told me, probably zero. I said, I agree. And I go, are you still seeing the problem? They're like, yep, we increased the inspection and we still see the problem. So now what have they done? they've added more variation into the process and didn't solve the problem. So now they're going to have more problems. So important part of this process is understanding what type of variation are we looking at. If we don't classify it correctly, then of course we're not going to solve it. And I see that's a huge issue in companies. So the variation is basically the differences between the individual outputs of a process. So it doesn't matter what the process is. It could be engineering, it could be purchasing, it could be a manufacturing process, it could be sales. Every process, right, has outcomes, and if the outcomes are different, then there's variation. And the inherent variation is common cause, assignable cause, and the total variation is the sum of the common cause and special cause. So if we look at a process, what is a process? We describe it by the IPO model, input, process, output. It's a series of actions or steps to take inputs and convert them into desired outputs. And the desired outputs, that desired output is defined by the customer or the next step in the process. So Dr. Deming had a statement. He said, if you can't describe what you're doing as a process, you don't know what you're doing. Okay, so we want to be able to describe the process in terms of input, actions it's doing, and output, and then we start to get a good picture of what the process looks like. So what we want is we want processes that are repeatable and reproducible. So repeatable means that when I'm performing the process, the consecutive outputs of that process are consistent. So a lot of people think of it like a manufacturing process where I'm producing a process. Let's just take an injection molding, right? So I cycle the machine, it injects the plastic into the mold, okay, and the mold opens up, the part comes out, right? So each time that a part comes out of that mold, I want to have a consistent result. So I want that part that's coming out of the mold to be consistent, part to part, cycle to cycle to cycle, right? That's a repeatable process. Then we can have a reproducible process. So let's just say I take that die and that molding process and I set up 3 weeks from now and I start running. I need to be able to reproduce exactly what I did today. So we want processes that are repeatable within this process and reproducible between when we run the processes. So some of the inputs might change. So I might have a different operator, I might have a different machine, I might have material from a different lot. Okay, so we want to be able to reproduce that depending on the different input that could change, right? That's our goal. So of course, processes that are repeatable and reproducible are reliable. So we need processes that are reliable. So what causes processes to be unreliable? It's the variation. So variation is the enemy to any process. So if we look at process variation, is all process variation bad? No, not all processes variation is bad. So Six Sigma is about identifying and eliminating the sources of variation that affects the processes and prevents the processes from achieving the expected results. So we need to understand what's acceptable variation, and the customer defines that. What's unacceptable variation, of course, the customer also defines that. We want all processes to operate within the acceptable variation range, okay? So if we look at variation and we look at a process, there are 6 sources that where variation can come from. So it could come from the people in the process, can come from the machine itself, can come from the method, can come from the material, the measurement, or the environment. So all variation can be categorized into one of these 6 categories. Okay, so the goal is to identify the variation that's causing the process to be unstable and reduce that variation. So when we talk about variation, we can look at statistics, and Sigma means standard deviation. So that's how many standard deviations of the data from the process. So if I look at this, if I take data from a process and I run a process, I measure the process. If I measure the process, I can take that data and I can chart it on what's called a histogram. The histogram, I can calculate different statistics. I can calculate the average, right, or the central limit, and I can calculate the range, so the smallest to the largest, and I can calculate the standard deviation. The standard deviation is the amount of variation in the process. And so Statistics says if I take the average and I take one standard deviation from the average, 68% of the data points should fall within that range. So in measuring parts per million, that means that 317,300 parts should fall. If I'm running 1 million parts, that many should fall within one standard deviation. Likewise, 2 standard deviations, 95.45, 3 standard deviations, 99.73. So let's just take that. What's the probability if I have a process that's within 3 standard deviations? What's the probability we're going to have a part fall outside that? So if I take that 0.73 divided by 2, because I got a 2-sided histogram here, so that gives me what, 0.27. So there's like a 0.135% chance I'm going to get a point outside the limit if it's operating normal, which is very, very small, which means 2,700 parts per million. So if I run 100, or if I run 1 million parts, I only expect 2,700 of them to be outside one of the limits. Now, as I move down the Sigma levels here, when I get to 6 Sigma, that means that we got 0.002 parts per million, right? So if I move that decimal point, so that means if I run 1 million parts, I'm going to have less than 1 that's defective, right? That's 6 Sigma. So that's having the process extremely, extremely tight, okay? So, of course, you're not going to get to 6 Sigma overnight. You're going to work through the progression, and what you want to do is you want to move down the progression of, let's get to 3 Sigma, 4 Sigma, 5 Sigma, until we get to 6 Sigma. But if we get to there, our defects are almost 0. Okay, so it's a problem-solving methodology. Again, our phases are define, measure, analyze, improve, control. So the first 3 phases, we can categorize them as process characterization, really understanding the process itself. The second pieces here are phase 4 and 5, are improve and control. That's really about optimizing the process. So we don't optimize the process or make changes to the process until we really understand the process itself. And the combination of process characterization and process optimization gives us that breakthrough strategy. So when we do a Six Sigma project, we're working through the 5 phases of the Six Sigma methodology. So let's talk about those phases now. So the first is our define. So that's defining the problem that we're going to work on. And so there's a project review stage where we define the project charter and establish the business case. So why would we want to focus on this process or this problem? What's that going to do for the business? So again, I see a lot of people skip this step. So it's like, if we understand what the KPIs are, the key performance indicators of the process, and we'll talk about this next week, is if we're going to do this project, which key performance indicator from the business are we going to affect? If it's not going to affect one of those key performance indicators, I'm going to question, why are you doing that initiative? Okay, so when we talked about theory of constraints, we talked about focus, right? Focus means doing what should be done and not doing what shouldn't be done. So the business case should be telling us what activities should we be doing to get breakthrough performance and which ones shouldn't we be doing that aren't going to affect the performance at all. Next is developing the problem statement. So the problem statement, again, most times I see people don't do a correct problem statement. So if we don't define the problem correctly, what's the chance we're going to solve it? My statement is slim to none. Then our goal statement. So once we establish the problem statement, then what are we trying to achieve? That's our goal statement. And then what's the scope? So what are the boundaries of the process that we're going to look at? So what's the starting boundary, the ending boundary, and make sure we stay within our boundaries. And then what are the prioritized customer requirements? So if we're not getting complete customer satisfaction, let's prioritize those customer requirements and make sure we understand from the customer's perspective how this problem is affecting them. Okay, so that's the first part of the define phase. So once we establish the project charter, we want to again, talk about that business case, do the problem statement, goal statement. Define our team members, so who's going to be working on the team. We want a cross-functional team that's made up of members from different areas of the business, and I like to have people that are familiar with the process and people that are not familiar with the process. So the people that aren't familiar with the process, the reason we have them on the team is because they're going to challenge what we're doing, right? Because when we get involved in the process for so long, we start to get blinders on and we can't see things that are abnormal conditions. So I worked with one company, and what I said to them, it's like, if problems become problems for so long, it becomes normal condition and people can't see it as a problem. So like I'll go in, I did some work with some construction companies. And so I go in the construction company, they said, oh, we do the project, we do all these activities. And then the last thing is to have a walkthrough with the customer. And then the customer finds all these problems. And so we create they call it a punch list. So at the end of the project, we have this punch list of everything that needs to be fixed. I go, you do what? Oh, it's like every construction company has a punch list. I go, yeah, just because everyone does it doesn't mean it's correct. So you can imagine in your business that you would send the product to the customer would inspect it and then say, oh, these are all the things I found that are wrong. It's like after the fact. I'm like, that's reactive problem solving, not proactive problem solving, right? The goal would be to have zero punch lists, right? That it's when the customer walks through, everything's correct, right? That's our future state. But they're like, well, that's never going to happen. It's like, okay, if you don't think it's going to happen, you're right. It's not going to happen, right? There's a statement that Henry Ford said, if you say you can or you say you can't, you're right. So just because something becomes a problem, don't take it as normal condition, because people have been conditioned that, oh, that's the way it is, but it doesn't need to be that way. Then establish what are the roles and responsibility of the team, and then what's our action plan and what's our budget. So are we going to be able to have a budget, and then are we able to achieve our action within that budget? So problem definition, what do we want to improve? Are we looking to reduce cost? Are we looking to reduce complaints, either internal or external? These are non-conformances. Are we looking to reduce defects? So this is typically product defects. These complaints are usually, could be non-conformances from the process. And of course, when we have increased costs due to overtime, expediting, wasted material, defects, right? What are we trying to achieve? So let's define our goals. And our problem definition needs to be based on qualitative facts supported by analytical data. So it's not just people's opinions. So Deming had another statement, without data, you're just another opinion. So we need data, we need facts that support our findings or our problem definition. And again, another mistake I see companies make. So define phase, we want to define the processes, define the customer requirements, and prioritize those customer requirements. So under the define the process step, I use a technique called process characterization. So this is also what Six Sigma uses. I'm actually a Six Sigma green belt. And so what we want to understand is what's the variables in the process and what's the variables of the product, okay, product or service. So process characterization is creating the link between the dependent and independent variables of the process, and then ranking their importance of the relationship. So it starts by identifying what those independent and dependent variables are in the process. So what are dependent variables? So these are the output variables of the process as a result of performing the process. It's the features of the product or service. So like if I go to buy a new car, right, I'm looking at what's the mileage that the car gets, like what's the warranty on the car, what's the, right, those are dependent variables. It's related to the product itself. Okay, so these are things that customers care about, and it can be measured by, and what can be measured on the product or service is being produced by the process. So for example, response time, on-time performance, the thickness, the diameter, surface finish, these are all outputs of the process that are characteristics of the product itself. So we take the product or service, we list all the characteristics that the customer cares about, and then we measure the process itself, and the variables in the process, we define those, and we can do that by using what we call the cause and effect diagram. And these are things that can be changed, right? So these variables can be changed. So I can change the machine speed or the pressure or how much lubrication is happening, the flow rate, the heat settings, exposure settings. So these are all variables from the process. So the example I gave about that company was they went and they changed the speeds and feeds, they changed the coolant pressure, the direction of the coolant pressure, right? Those are all variables in the process. So if you start to look at your organization, you can start to define what are variables that are in the process, what are the characteristics of the product or service, and then what we want to do is we want to map the relationship between those. So for example, if I go back here to, thickness, right? So thickness is one of the characteristics of the product. How does speed relate to thickness, right? So the machine setting speed, does that affect thickness or not? So what we're doing is we're ranking that on a scale of 1 to 10. So we start to understand the critical few. So the Pareto principle said that 20% of the variables are affecting 80% of the outputs. Okay, so we don't need to focus on every variable in the process. We need to narrow it down to a critical few. So depending on how your problem is defined, you're going to define those independent and dependent variables, and then you're going to show the relationship of those and how that's related to the problem itself. So this is an extremely powerful tool if you do it correctly. So once we define the problem, we got our problem statement, we understand the variables in the process, we understand the relationship of the variables to the customer requirements, then we want to go to the measure phase. So the measure phase is identifying the measurement and variation, determining the type of data that we're going to work on, and developing our data collection plan. So we want to collect data about the process. So how are we going to measure that? Of course, we need to make sure if we're measuring it that our measurement system is actually capable. What type of data are we going to collect? So there's two types of data, what we call what's the data types? Lost it here for a second. So two types of data are attribute and variable. So attribute data is data that we count. Variable data is that we have to measure it with some measuring device. So if I look at the characteristics of myself, what is attribute data? So attribute data is things that I count. So I can say, okay, if I'm in a room of people, how many people have blue eyes? How many people have brown eyes, right? That's attribute data. Variable data is data that I can measure. So it's like, okay, what's my height? What's my weight, right? What's my blood pressure? I need a device to measure that. That's variable data. So we need to determine what type of data we're going to collect and then develop our collection plan. Then we're going to measure our measurement system and see if it's actually capable of measuring that accurately and precisely. That's a whole session in itself. And then we're going to collect our data. Then we're going to perform our capability analysis. So how is the process performing today? So what's the effectiveness of the existing process? Let's calculate our sigma level. So how much variation is in the process according to that chart that I showed earlier. And then let's calculate our cost of poor quality. So if we're not able to meet the customer requirements, how much is that costing us as an organization? So if we look at process capability, it measures how well the process is capable of meeting the customer specifications. So there's specification limits that are defined by the customer. So these are the limits the customer defines as acceptable, that has the acceptable tolerance. And then there are the control limits that are determined by the process. So these are the limits that are calculated from the output of the process. So when we compare the two, so we're comparing the specification limits to the control limits, that determines our process capability. So an example would be, I'm going to go purchase some beer, right? And it's like, I expect in the beer, a 12-ounce can. So when I buy it, am I getting exactly 12 ounces? Probably not. I'm probably getting either a little bit more or a little bit less. So what's my tolerance? So it's like, I definitely don't want to buy a can that's half full, right? So if I'm going to pay for a full 12-ounce can, I want full 12 ounces, right? So what's my limit? Well, maybe 11 ounces is my limit. If the can is less than 11 ounces, I'm not going to buy it, right? That's my specification limit that I'm defining of what's acceptable to me and what's not acceptable. Now, when they fill the beer in the can, how well are they able to fill it to 12 ounces? Okay, so what does the process actually hold? So maybe the process can hold a tolerance of, 11.8 to 12.2. Okay, so we never have a can less than 11.8, and my tolerance is 11. Okay, that's acceptable for me, so that's capable. Okay, so what we're doing is we're comparing those limits that are defined by the customer to the limits that are defined by the process. And there's two measures, CP and CPK. For short term, long term is PP and PPK. So just CP is what's called the process potential. So we're measuring our customer specification limits to our process control limits. And we're looking at the relationship of these two distributions. So a high CP, a high process potential, would be that the control limits of the process are way inside our customer spec limits. Okay, so all we're doing is comparing the width of this one distribution to the width of the second distribution. Now, in this case, if the customer specification tolerance is much wider than our process control, we have a high process potential. It still doesn't tell us if we're capable. Okay, so it measures the process precision, but what we really need to understand is the capability. So capability measures what we call precision and accuracy. So it's measuring not only what the relationship is how centered is the process. So you see this diagram to the right here. I have the process control limits are wide, the customer specs are wide, the process control limits are narrow. So I have a low CPK because it's not centered. So this example to the right, my CP value is high, my CPK value is low. On this one to the left, my CP and my CPK are high because my customer, so the process control limits are outside the customer spec. So we're going to have a lot of product that's outside of the customer spec that's going to be scrap. Okay, so when we're looking at process capability, you have to use the two in combination. So I might have a customer call me up and say, we got a problem with a lot of scrap on this process. And I said, okay, did you measure the process capability? They're like, yep. So I said, okay, my first question is always, what's the CPK? And they say, the CPK is 0.8. Okay. So my second question always is, what's the CP? So they say, the CP is 1.5. Okay, so from those two data points, I can tell whether they have a precision issue or an accuracy issue because the techniques to solve a precision issue are different than the techniques to solve an accuracy issue. So in that case, where we have a CPK of 0.8 and a CP of 1.5, I have a centering problem. I got this issue right here. So I need to get the process centered. So I have precision, I have an accuracy problem. Okay. So I don't expect you to remember that, but it's like once you start to learn statistics, you can understand the process and how to analyze it and then what actions to take just from the data. So this analyze phase, we're taking that data, we're analyzing it, we're analyzing the process, we're formulating a hypothesis about where's the variation coming from, and then we're going to test that hypothesis. So we test the hypothesis by actually changing variables in the process and see if it improves and reduces the variability in the process. So every problem solving process you go through, you're going to have a hypothesis And then you need to validate that hypothesis, whether it's correct or not. If the hypothesis is not correct, you need to go back and reformulate your hypothesis and then retest. Because, and I see that a lot in problem solving, where people have a hypothesis when they do their 5 why, and they get to the second why, they don't validate it with data, and they just assume it's correct, and they go down to the 3rd why, 4th why, 5th why, they implement some countermeasure, and the problem doesn't go away. Because one of the steps they didn't validate, and it's not a valid solution to the problem. So this is extremely important. And when we're going through the Six Sigma process, just like problem solving, we're going to spend the majority of our time in this define, measure, analyze stage, right? So that process characterization we talked about, I spend probably 80% of my time in that stage and 20% in the improved control. Because if we really understand the process and we really understand where's the variation coming from, and we do our homework and we formulate our hypothesis and we test it, then we're guaranteed that when we make the improvement, that the variation is going to reduce. Okay, so we want to spend most of our time in these first 3 steps. So the basic tools for analysis that I use in these steps are histogram, Pareto chart, flow chart, cause and effect diagram, and scatter diagram. So these tools are 90% of the tools I use whenever analyzing a problem or a system. And you can gather a lot of information about the process just using these tools. And again, this is a whole nother session just going through these tools and how to use them and what it's telling you. Okay, so the basic is histogram is the voice of the process. So the histogram gives us information about how the process is performing. Pareto chart, Pareto told us that the 80-20 rule. So any process is controlled. There's, if there's 100 variables, 20 of those variables are controlling 80% of the process. Flowchart is a way to visually map out the whole process start to finish. Cause and effect diagram tells us where the variables are in the process. Scatter diagram tells us the relationship between 2 variables. So I have a quick story about the scatter diagrams. I was doing problem solving with one company, and they had a problem with so they had a heat exchanger. So the heat exchanger typically would go 7 days before they had to clean it, because the U value got down below a certain level, and then the heat wasn't exchanging at the rate that they need. So they got to stop the process and clean out the heat exchanger. So we start doing the process, and we started defining our problems. We get a problem statement, and they said, well, we know what the cause is. I said, well, what do you think the cause is? So, well, the operators that are cleaning it, because there's pressure to get it up and running, that they don't get it fully cleaned. And if they don't clean it, then we're getting to a lower U value in a shorter period of time, and then we got to take it down. I said, okay, let's take data and look at it, right? So I said, do we know what the U value was before we cleaned it? They're like, yep, we know that. Do we know what day we cleaned it? Yep, we know that. Do we know what the U value was after we cleaned it? Yep, we know that. And then do we know when the next cleaning happened? Yep, we know that. So we took the data and we took 2 variables. We said, okay, the starting U value. So after they cleaned it, what was the U value? And then how many days it went till it had to be cleaned again. So when the U value got down below the acceptable limit. So we did a scatter diagram, and what we found, absolutely 0 correlation. So what that means is their assumption wasn't correct. It's like, that's not your problem. But they were sure, it's like, the operators, if they would just clean it better, we wouldn't have this problem. That's not the issue. Okay, so this tools help us differentiate people's opinions and the facts about the process. So then the improvement phase means to identify and remove all causes of variation. So we want to understand what are those variables, key variables in the process, identify the acceptable ranges for those key variables. Then we want to modify the process to stay within those acceptable ranges. So this is our process improvement. So we're going to generate improvement alternatives. So what can we do to improve the process and reduce the variability? Then we're going to validate that. So we're going to implement the countermeasure. We're going to take data again to see if the process improved. Again, speak with data, then create a future state process map. So how should the process, so if the improvement actually solved the problem, then we want to create that process map of the new process, the future state of how the process should be operating, and then validate our cost benefit analysis. So what's the benefit to the organization? What did it cost us to implement that solution? And again, we're looking at reducing the variability. So we're going to move down this Six Sigma progression, right? So we might be at 2 Sigma, we can move to 3 Sigma, we're going to move to 4 Sigma. Very rarely am I going to see people go from 2 Sigma to 6 Sigma, right? You're probably going to go from 2, maybe to 4 if you do it really well. Then, okay, if it's still a problem, we need to go to the next level. Okay, so our improvement phase, we're doing the project review, we're validating the pilot study, we're doing our cost benefit analysis, we're putting the plan for our control phase in place. And the control phase is how to sustain the improvement. So this is key, right? So we don't want to go through all this analysis, all this activity, and then put the countermeasure in place, and then 3 months later, slipping back to old practices. So this is one of the hardest steps because people are creatures of habit. So in order to get change, we need to change people's behavior. Behavior modification is not easy. And again, it's a function of how long people have been at the company. So I was in one company and we're going through a whole plan to improve the flow, and we come up with some different ideas on how to do that. And when I went around the room and asked people how long they've been at the company, it was like 40 years, 38 years, 32 years, 28 years. It's like nobody was less than 25 years. And they're like, how hard is this going to be? I'm going, it's going to be hard because people are conditioned. You know, you got multiple years of conditioning doing it one way. Now we need to change. It's not an overnight solution. It could be months to get the process to sustain. So what we want to do is we want to make sure that the process stays within our control limits, and those control limits are within our specification limits for the customer. So what are the tools we need to do that? So in the control phase, we want to develop that control strategy, develop our control plan, update our procedures and our training plan, monitor the results. And if we're not sustaining, then put in corrective action to go back and the improve step, and then control again. So process monitoring techniques are used to sustain the gains. The techniques that I use here, a run chart's a good technique to do that, an hour-by-hour monitoring chart, a statistical process control chart, visual controls, daily walk process, and process audits. So these are techniques to help us sustain the gain. And again, we're going to use a combination of these, or we're going to use one, depending on what the process is. You choose the right technique to be able to monitor that process. So I'm big on visual controls. I'm big on the daily walk process. These others are dependent on the process itself. So one company I was with we had a problem with there was a big rush at the end of the day. So they're a distribution company. There was a big rush at the end of the day to get stuff packed to make it to the truck. And so I start watching what people are doing, and I go to the warehouse manager. I said, you know what? Batching is terrible for productivity. He's like, what? I go, batching is terrible for productivity. He goes, what do you mean? I said, watch what your people are doing. They're taking all the orders and they're picking multiple orders at a time all morning. Then they're taking them to the pack out table, and the guy at the pack table doesn't have anything to do in the morning, and afternoon he's like pulling his hair out because he's like overwhelmed with stuff that needs to get packed. He's like, oh, that's not happening. So okay, well, let's put an hour-by-hour chart in, and let's have the guy in pack out, right, every hour, how many boxes he packed. So typically they're doing like 150 boxes a day. So we put the hour by hour chart in place. We go out at lunchtime, so they start at 7. So it's 5 hours into the shift, and he packed 3 orders. So I said to the warehouse manager, so you don't think your people are batching their work? He's like, oh my God. So then, of course, he's packing like 140 some orders in 3 hours, right? So that's why he was going crazy. And they had issues with sending wrong products to the wrong customers, errors on the orders, right? So because everyone's rushed. So we said the concept is pick one, pack one. Pick one, pack one. So then we started training the people. It's like, we want you to pick one order, take it to the pack out table, go pick the second order. They're like, yeah, but that's not efficient for us. Right. And I said, our goal isn't to make you efficient. What's our goal? Is to pack all the orders throughout the day with 0 quality issues. So when we went to pick one, pack one, and we looked at hour by hour chart, you know what? The first hour he packed orders, right? And so our return for incorrect orders like cut in half, and we eliminated overtime, right? So those simple techniques using that hour by hour chart gave us the data and made us look at the process, and then we changed the process and improved the system. Okay, so extremely powerful techniques to sustain the gains. Okay, so that's our session for today. Again, we are doing this in conjunction with the Northern Pennsylvania Regional College. And if you want more information on training, so we do all types of training on these techniques, operational excellence, lean, Six Sigma techniques, problem solving, SPC, you can reach out to the Northern Pennsylvania Regional College. Their website's here. Again, if you want to connect with me on LinkedIn, I post information every week on different concepts, and visit our website, and from there you can see all our posts. And we also have a YouTube channel, so you can search for our YouTube channel. We got literally hundreds of videos, I think, now on different topics.